So I'm going to give kind of a broad overview of what the Verilog-to-Routing project is about, and dive into a few recent accomplishments, and then talk towards the end about. Let's see if I can make these slides advance. Talk towards the end about some enhancements that are underway now, but in the early stages for the Crossroads 3D FPGA, which is the focus area for this seminar series. Um, I'm not going to go through all the agenda here, but that's the high level view of what I'm doing. And I'm presenting the work of many people who've worked on VTR. So I'd like to just acknowledge all of their work. And Kevin Murray and Mohammed Al Gamal in particular, I've grabbed slides from some of their work to bring up this talk. Okay, so VTR is an open source CAD flow, and its hallmark, its kind of driving purpose is to be flexible, to be able to change the architecture that it targets quickly and relatively easily. So, why? Why is that a goal? And then what challenges does that bring up? So the first big driver for VTR to exist is FPGA architecture research. So you can't come up with a better FPGA architecture with just analytical models. You have to apply an empirical method because basically it's too complex to model the whole thing analytically. So the standard flow is to use benchmarks, target different FPGA architectures, different ideas that you have, and see how well those benchmarks perform in each one of those architectures that you're proposing. So that means that you need a high quality CAD flow, and you need it for every architecture variant that you want to evaluate. And developing a CAD flow is a very large undertaking. So this is a major barrier to actually looking at different FPGA architectures. So VTR's number one purpose has been to address that gap. Give us a CAD flow that can be retargeted at different FPGA architectures. Now, a question you might ask, well, why do we need new FPGA architectures? Maybe we don't. Maybe we can just keep producing bigger versions of the same thing over and over again. And there are a few reasons that doesn't work really well. The first thing is the process technology changes. So FPGAs are early adopters of advanced process technology because FPGAs use a lot of transistors, so they really crave more density. As you move to newer process nodes, wire resistance is changing, power limits are becoming a bigger deal. We're getting disruptive effects like interposers becoming a new option. So that's an entirely new thing. So our implementation medium is changing in significant ways. And really we want our architectures to get the most out of that implementation medium, so they have to change too. Second thing that changes is what we're doing in these chips changes. So we get new standards, we get faster processing. So we're moving from 4G to 5G. Deep learning has become an incredibly important new workload, and it's evolving very quickly. FPGAs are being deployed not just as standalone monolithic devices anymore, but there's also a lot of interest in embedded FPGAs. So putting an FPGA fabric inside a larger SoC. And that actually exists in some products that you might not even know about. So there are products that I know, for example, are using VTR under the hood, where the chip is marketed as if it is just a very flexible microcontroller or a very flexible chip for certain control applications. But under the hood, it actually has more than just a microcontroller. It's also got some FPGA fabric. The Cypress PSOC is another example of that. And there's a lot of interest in embedded FPGAs potentially moving into other systems on chip. And then the last thing is just innovative architecture ideas. You've got a new idea of how you could make a better chip. How are you going to test that out? So I don't think FPGA architecture is going to stabilize anytime soon. We're finding certain design styles work well, but I don't think we are ever going to find that we can just say, we're done. We know what it is forever. Okay, so that was the first big driver of VTR. Second one is FPGA CAD research. So I have an idea for a new CAD algorithm. Maybe I've got an idea for something new in placement. So I've just circled the box that is placement in this CAD flow. You need a whole infrastructure, you need benchmark circuits to evaluate it. Building that whole thing from scratch is a major undertaking, and that's not your main goal. So VTR allows you to just replace or augment some CAD algorithm and see how well it works. By having a common framework, it also allows you to compare results more easily. And finally, if you come up with a better algorithm, let's say for placement, it has more impact if you put it into an existing flexible tool like VTR. There's a project called SymbaFlow, which will produce bit streams for several commercial FPGAs from a completely open source CAD flow built on top of VTR. There are startups that use VTR as their internal placement and routing engine, and it helps architecture researchers and so on. So it's less work to test your algorithm, you get a better comparison to prior results, and others can build on it more easily. Okay, and the third use of VTR that's become more important recently is to actually program your novel architecture. So you've decided I need a new architecture, you create the layout. How are you going to program it? So building a CAD flow is usually the hardest part of entering the FPGA industry. So a couple of examples here. Here is a novel imager from the MIT Lincoln Lab. It combines a customized FPGA with a spatial image detector, and that needs custom CAD. And their CAD is built by targeting VTR at that chip. On the right-hand side, I'm showing OpenFPGA, which is developed at the University of Utah. And this is a fabric generator. It actually takes the architecture that is created by VTR, so it takes the detailed data structures and uses those to drive a layout generator. They create a layout, and they have the programming flow for it as well. And the PRGA project at Princeton follows a somewhat similar approach, and there are others. So this has become another important use of the tool. Okay, so hopefully that's enough motivation. You're convinced, yeah, we should build CAD tools like this. So let me talk about what is in Verilog-to-Routing. So it's actually several tools, and it's actually more than one flow. So I'm showing you the most common flow that people use with VTR. This would be kind of the end-to-end, completely open source VTR CAD flow. Verilog goes in, so your design, or maybe you have a set of benchmark designs, and an architecture goes in. So the architecture is described in one or more files so that it's also highly flexible. A couple of tools do the front-end synthesis. So Odin 2 understands the Verilog language. ABC is the logic synthesis tool from Berkeley. So it optimizes and technology maps to lookup tables. Odin 2 basically finds the hard blocks like RAMs and DSPs and so on and protects them so ABC doesn't change them. Out of that comes a netlist. And then netlist drives the VPR tool, which does basically the physical implementation. And it proceeds in four phases. Packing, which groups little things, primitives, into larger blocks like logic blocks or DSP blocks. Placement, which chooses where to put each of those. Routing, which wires them together. And finally, analysis, area, delay, and if you'd like, power. And all of those things are timing driven. So every one of those algorithms actually constantly talking to static timing analysis to see is this fast or not. Being timing driven is very important in the FPGA world. I think even more important than it is in the ASIC world, because once you're done routing, there's generally nothing you can do to fix timing violations. Whereas in the ASIC world, you could actually go and do some gate sizing and some final fix-up steps. So if you don't solve all your timing problems at the end of this flow, you're in trouble. Okay, so what are the challenges with that flow? We're kind of trying to achieve three things. Architecture generality, so we can easily change the architecture. We also would like high quality, and we would like to have fast run times. So can we actually have all three of those things? And each one of those is a significant challenge. So I'm not going to give you a perfect answer. I'm going to show you some results that suggest we can have at least a pretty good compromise between all three of those. It's an open question, and maybe it's impossible to have the best results in all three of those simultaneously. So I'm going to now talk a bit more about what's gone in the most recent kind of production release of VTR, the 8.0 release. So what are some new capabilities and features? A big change was how the router works. So I'll talk in some depth about the routing algorithm that it's using. We have also made some other enhancements to the overall CAD flow. And finally, I'll talk a bit about an algorithmic enhancement we made in placement that uses reinforcement learning. So kind of jumping around the CAD flow, talking about different enhancements that came out in the most recent release. Okay, so let's talk first about capabilities. So what comes out of the first part of that VTR flow is primitives. So synthesis maps to lookup tables, multipliers, RAM blocks, and so on. And in VTR, you can specify essentially arbitrary primitives. So what are they? Lookup tables? Are they a certain size? Are they AND gates? You can do whatever you like there. You can combine those logic elements into, or those logic primitives hierarchically into larger physical structures. So you might have logic elements that combine a few lookup tables and registers. You might have logic blocks that combine now several of those logic elements, and they could have local interconnect within them. And you can specify all of that. And it's not just for logic blocks. The same approach is used for RAM blocks, DSP blocks, and kind of other things that don't really have a name. You're not limited to those types of blocks. So it's quite flexible in how you model the blocks. Okay, once you've decided, okay, these are the primitives that my chip's going to support, and this is how they're arranged into somewhat bigger blocks, you describe how is that laid out on the chip, what we call the grid. So, for example, I might decide that I'm a cheaper FPGA and my IOs are around the perimeter. And inside I've got logic blocks. I might decide I've got one big hard block, a processor subsystem. There's just one of those. I've got some other keywords saying just fill this whole region with something, maybe logic blocks, and so on. So there's a bunch of easy to use keywords to kind of specify what is the two-dimensional arrangement of these blocks that I've defined in the chip. Okay, so this would be an example of a chip you could describe pretty succinctly. It's got a mix of logic blocks, DSP blocks, RAM blocks. Some of them are larger than other things. The IOs in this particular case are around the edge, and we've inserted NOC routers, okay, which are put in sort of in an overlaid mesh on top of the rest of the resources by pushing things out of the way, and we've got a PCIe block over here. So it's pretty easy to describe what is the layout of my chip. Okay, that's not enough. We need to know how does the programmable routing work. So this is a picture. All these pictures are taken directly from the graphics in the tool. You describe how do my blocks connect to the routing wires that are near them? Do they connect to some of the wires, a lot of the wires? Do they connect on all the sides, or on certain sides, etc.? And you describe how long those wires are, what their physical characteristics are, and the exact pattern of switches that you have between the wires as well as their electrical characteristics. So it's a pretty flexible description of the routing. And in VTR 8, it's much more flexible than it was in previous versions. Some of the ways that it's been made more flexible in VTR 8 is when you have those large blocks, like that processor subsystem that I talked about, you have a question of, well, did that processor subsystem block all the wires that went across it? Did it not block the wires? Maybe some of the wires can actually go across it, the usual programmable routing, but none of the switches are there. We didn't want to interfere with the layout of that hard processor subsystem. So we managed to get some wires on the top level metal across it, but we took all the switches out between them. So you can say that's the way you did it. Or you could say, I actually couldn't get the wires across. They're interrupted. The CAD tool has to accept that. Or maybe I was able to actually put everything in. It just doesn't interrupt the routing fabric at all. I'm not going to go to the details of the whole specification, but you can describe wire connectivity in much more detail than you could in prior versions of VTR. That takes more text, so it takes a little more effort, but you can do it. And something else we added are what we call non-configurable edges down here. So a non-configurable edge is you could have a long wire where you actually put non-programmable, so non-tristatable buffers in the middle of it for electrical reasons. And you can now specify that, and it'll go in the architecture, the router will use it. You can also use that to specify complex wire shapes, like this is an L-shaped wire, by saying that you've shorted them together. So there's a non-configurable edge that is actually a piece of metal between them. The last level of configurability is what I've described is basically in the architecture specification language. But we found some users of VTR basically want even more flexibility. So they've taped out a chip like that MIT Reimagine project or OpenFPGA or some of the startups using it, and they don't ever want the pattern of wires and switches to change because they've already committed it to silicon. But they'd like to move to newer versions of the tool, or maybe they're targeting an existing commercial FPGA, so they know what the pattern of wires and switches are, and they need it to be exactly match that. So for those cases, you can now load in the very detailed, very large, this is usually gigabytes in size, representation of all of the routing in the chip. And you can just load it in as a flat graph from disk. So that gives you full control if you have something that doesn't fit in that architecture specification language that I mentioned, or you just never want it to change. We also put a bunch of work into making more flexible and more powerful analysis and modeling. So you can now run timing analysis, area analysis, power analysis independently of optimization. So more like a typical commercial flow. You can implement your design and then decide to do what-if analyses without changing the implementation. Added more visualization reporting, better area models, and the timing analyzer in particular is more full-featured. So it can do both minimum delay and maximum delay timing analysis. It can handle multiple clocks, both within blocks and within a design well. It handles a subset of the Synopsys design constraints. So you also control it using industry standard scripts. It doesn't support every feature of SDC, but it does support the most common and important ones in terms of timing constraining your design. And I'm showing just a few pictures that come from the CAD tool to show how you could visualize things like where's the critical path, what's the routing utilization, a report that comes from the timing analyzer, and so on. Okay, so that was all about new features. And I apologize if I'm going pretty fast. I have quite a few slides. So at the end of this, you can tell me whether it was way too fast or not. Or James, you can jump in if you think no one can possibly follow. One of the things we did in VTR 8 is put quite a bit of effort into the router, trying to make it faster. So we gave it a name, AIR, or Adaptive Incremental Router. So for those not familiar with it, the FPGA routing problem is generally modeled as a graph. So I just talked about that routing resource graph. The nodes in that graph are conductors. So they can be wires like this, or they could be pins, so inputs and outputs of various blocks. And the edges are the configurable switches, or as I mentioned, we now also have the ability to model non-configurable switches, which are buffers that you can't turn on or off, or metal shorts to make more complicated wire shapes. So the routing problem is we need to find an embedding of the netlist, so the connections that need to be completed by your design inside that RR graph. So that basically the first step of what I described is we turn your specification, something like this, into a graph. So this is the routing resource graph. And we have sources and nets, basically, that come from your design. So if you have a design that says I need to connect this node F to this node J, we need to find a path through this graph to do it. So we need to find a lot of non-overlapping trees in this RR graph. We want to minimize the delay, so make our circuit as fast as possible, particularly on the critical path, things that our timing analyzer said are critical. We'd also like to minimize the amount of wiring, first so we don't run out of it, and secondly to minimize power. Because these graphs are very large, millions of nodes, and we're searching for hundreds of thousands or even millions of trees within them, runtime's a big issue. So keeping runtime reasonable is a challenge. And generally, unlike ASICs, this is solved as a single combined global detailed routing stage. There are different approaches you can use here, but basically creating a hard boundary between global routing, where you say, I'm going to choose what channel I'm in, and then detailed routing, where you choose which wire you're using, is more challenging in FPGAs because this graph is less flexible than what you would have in an ASIC problem where you can put metal anywhere. So you have to be careful if you use a global router that you don't over-constrain the later detailed router. So we solve it, which is the more conventional approach, as a single combined search through the whole routing graph. So the overall algorithm we use is called negotiated congestion. So it's pioneered by a tool called Pathfinder. It allows multiple nets to use the same routing resources, which was called congestion. And then these nets negotiate for resources. Instead of blocking each other, they just essentially cause an increase in cost. So it's allowed to have congestion, and the tool can monitor it and gradually works to resolve it. Okay, so that's conventional for the FPGA problem. And the usual way this is completed is your innermost loop is what's called a connection router. So a connection router would take a single connection. So I want to go from this output to this input, and I need to find a path. Once I've found that path, if this was a net that had more than one connection, so this net has another connection that needs to go to this input, I now search for a path that branches off what I've done so far and completes that second connection, and so on. If there's a third, if this was a fan out 3 net, I'd have a third connection to route. Okay, so we route every connection within a net, one at a time, and then we route every net in the design. So these other nets are now being routed, and they have to make sure that they negotiate and try to not use the same resources as those earlier nets. We check after we've done this for all of the nets in the design, is it legal? So if they use some of the same resources or there's congestion, then it's not legal. If it is illegal, we have to rip up some of the nets or all of the nets, increase the congestion costs, and try again. Okay, so in this case, we have some congestion because these nets are using some of the same nodes or wires, and it'd be illegal. We'd have to rip it up and reroute. And the typical approach has been to rip up, initially the approach people used was rip up all the nets every time. That was gradually refined to let's just rip up the nets that are involved in congestion. But you wind up usually doing a lot of rerouting. So there's a lot of rip up and reroute, and this iterates many times, and that can be slow. So eventually, if you keep rerouting and you keep increasing the cost of the congested nodes, you have a high probability of getting to a legal routing. Okay, so what does AIR do? So it's a negotiated congestion router, so that's well known. It does two things that are new. So it tries to be more adaptive to improve quality and robustness. So that really links into the adapt to the architecture automatically, and it tries to be lazy. Don't do as much work that is redundant. Okay, so how does that work? So the innermost loop here was this connection router. Try to find how to hook up the, from this output to this input. And the approach we use, which is very similar to the original Pathfinder, is we basically know what the cost is of all the resources we've used to a certain node as we're searching through the graph. So we started at S, we've gotten to N, we know how we got there. We can keep track of all of their costs, including their congestion. We don't know what's going to happen in the future. And to explore the graph efficiently, we need to have a good estimate of that. What's going to happen in the future to see, is this actually a promising partial solution that we should keep expanding or not? Okay. And we also have to add in the cost of the node that we're considering adding right now. Okay, so I'm not going to go through all the details of this, but basically the cost is a function of both how much are we using, how much resource cost, and how much delay cost. And that's balanced based on how critical the connection is. So what AIR does is this expected cost adapts to the architecture better. We also make this base cost adapt to the architecture, but I'm not going to talk about that. So you can see the Asia Pacific DAC paper if you'd like to know more about that. Okay, so that figure out the expected cost is called a look ahead. Guess what's going to happen from a certain point in the routing architecture to your target. And that look ahead should adapt to the routing architecture. So the earlier VTR look ahead basically made some simplifying assumptions about how will wires connect, essentially to boil down to that the future will look a lot like the past. There'll be a lot of regularity. So, and we would get for the architecture I'm showing here, which has a mix of short wires, length 4, and long wires, length 16. But there's limited connectivity to the length 16 wires. They're kind of a higher level routing hierarchy that is harder to get on and off of. VTR would produce a look-ahead delay map. So this is just for delay, not for congestion, but it produces another map similar for congestion that basically says if I'm here on a certain kind of wire and I'm trying to guess how much delay am I going to take to get, for example, here, that would be about 4 nanoseconds. And that's actually not that accurate for this architecture because you have multiple options. You can actually hop from the short wires onto these longer wires. And in VTR 8, it basically explores the routing graph in an efficient way using something that's kind of like a router, but it's a Dijkstra flood algorithm. to efficiently find maps that incorporate information about all the routing choices. So in VTR8, the look-ahead map looks different. It understands that from this point, it actually could get out here in about 2 nanoseconds because it has the option of going from the short wires onto the long wires and back again. And none of that is hard-coded. It basically just automatically adapts to whatever routing graph you give it. And the challenge is to make it do that in a reasonable runtime, but it does do that. Okay, so that's increasing the adaptability of the tool. The lazy part of it is it tries to do much less rip up and much less exploration of the graph. So the first thing it does is it's lazy about routing nets. So a lot of the routing time we found was spent on high fan-out nets. So we are more incremental in how we reroute those. So for a high fan-out net, the standard approach is when you're going to route a connection on a high fan-out net is I've got a lot of previous routing. So all these black wire segments have already been put into the routing tree so far based on connecting previous connections that are part of this net. And I would use some kind of sorting structure to figure out how should I branch off of this to get to my new target. And we found that even looking once at all of these previously used routing segments took a significant fraction of our runtime. So we don't even want to look at this part of the routing tree when we're routing this one if we don't have to. So we use a spatial sorting structure that allows us to not even look at most of the routing tree as we're connecting it to more and more connections. So on the left, I'm showing the amount of routing graph that was examined, so looked at, in order to connect up one more connection on a high fan-out net. So this net has, I don't remember the exact number of terminals, but a large number of terminals. And the net's large, and we look at a lot of different nodes just to make a small extra connection. With the spatial lookup structure that we're now using, we look at a very small fraction of it, and that speeds up high fan-out net routing a lot. And this is made fairly adaptive. The danger in doing this is maybe you don't find a solution because you don't look at enough at the net. So we monitor how that's going. And if we're having trouble, we'll gradually expand the amount of the spatial grid that we will allow to be examined. Okay, so we also made the router more lazy by making it more incremental. So for high fan-out nets, we found that they're very frequently involved in congestion because they go to so many places, so they're ripped up a lot. But when they're ripped up, most of the time, most of the net is actually legal. So then a high fan-out net essentially is composed of many connections to many sinks. So what we do in AIR is we go find how much of this net is legal. What's the largest amount of it that we could keep? And we won't rip up that part. We'll only rip up the minimum part we have to. So let's say we are starting at A, that's the source of our net. We're routing through some wires and we have to get to these triangles. So in this particular case, we need to get to 4 destinations. And we have congestion only in one spot at node E. So traditionally, you'd rip up the whole net and try again. What we do in AIR instead is we figure out this subtree is the only part that really needs to be ripped up. So we'll rip up that subtree and reroute these 2 connections. And that works pretty well. The challenge is it sometimes can degrade your critical path because you're limiting your search of how you can reroute this net. So again, we make the tool adaptive by monitoring for that. And if it's finding that we have a problem, we're degrading the critical path, it basically increases the amount of the net that is ripped up. Okay, this is basically, I guess, what I just said. Okay, so let me just evaluate that router. How well does it work? So we took a series of large benchmarks called the Titan benchmarks. They range from 90,000 to 1.9 million primitives, so they're pretty big. They go through, in this case, we're not using the full open source flow. We're using the VPR place and route tool, but we're using Quartus for logic synthesis because these designs use a lot of IP and a lot of Verilog language features, so it's a lot easier to get them through the Quartus synthesis tool. And then we compared 3 academic routers. The previous version of VPR, a tool from Ghent called CRoute or Connection Route, and AIR. So what we found is that air is a lot faster than the previous version of VPR. It's about 7x faster, 6.6x faster. And it's also significantly faster than C-Route. So C-Route is another router that was published trying to really be more efficient by focusing more on connections. It does achieve a significant speed up, but air achieves even more. The critical path delay we achieve is better. This is on an architecture with a relatively complex routing architecture, a mix of long and short wires arranged in a hierarchy, as I showed you. And for an architecture like that, the smarter look ahead and the adaptable rip up give us a better critical path. So we actually get a better result than VPR7 and a better result than C-Route. And the routed wire length is also superior. So overall, it looks very good. And another thing that you can check with a negotiated congestion router is, what did it cost me to resolve congestion? So when we go from the initial routing, where we pay no attention to congestion, we're just trying to see what's the fastest we could connect everything, the minimum critical path delay. That's illegal. But that light blue line is how large would the critical path delay be if we were actually allowed to have congestion. And we find that when we resolve congestion, on average, we don't really move that critical path delay across that suite of Titan benchmarks. The routed wire length actually goes down as we resolve congestion. And the reason is that basically on parts of the design that are less timing critical, it'll actually the high fan-out nets will essentially reroute themselves to try to share wiring more where they can without affecting timing. So we can also see that it's resolving congestion well, despite the fact that we're trying to take a lot of shortcuts. Okay, so that was about routing. I'm going to tell you a little bit briefly about other quality enhancements in VTR8. Again, comparing on those 23 large Titan designs and using a channel width of 300, which is about what Stratix 4 has, VTR7 could only route 14 of them. VTR8 could route 23, so significantly better. Cordis 18 could actually route most of them. It had one of them that was unroutable and had two where just the device isn't big enough, where Cordis has no hope. And the pictures here are just showing, what does the congestion look like for these different designs? And there's significantly less congestion in VTR8 than VTR7. And the other interesting thing is that the congestion maps look pretty different for different designs. So it shows that having a diversity of benchmarks is pretty important to tuning your tools. Some of them, like this Bitcoin one, look pretty regular because they're soft logic dominated. But other ones, you can see that it's the hard blocks, which are in columns in the Stratix 4 architecture, are really changing the nature of the placement problem quite a bit. Okay, so we got a better result in VTR8 than in VTR7. It's significantly better. Some of that comes from the router, but not all. So we made a couple of other significant enhancements at a high level. So I'm not going to go into the details, but basically VTR does this packing of primitives into larger blocks, and then it places them. So in packing, we made it focus more on creating essentially natural clusters. So the challenge with packing things into logic blocks before you've done placement is to make sure that you don't combine things that don't really belong together. So in a design, if we had this set of circuit primitives, you can see there's kind of three natural clusters. And in VTR7, it would often take pieces of this third cluster, the one in the middle, and split it across two logic blocks, for example. And that's going to wind up stretching wires when you go and place the logic blocks. VPR8 tries hard not to do that, tries to find more natural clusters, which does tend to increase the number of logic blocks and RAM blocks and so on moderately. It's usually by about a low percentage, but not a 0%. But that reduces the wire length significantly. And the placement engine is basically iterative. So it basically is simulated annealing based. It's moving things around. And we changed how it explores the space, how it perturbs to be more efficient, particularly for things like carry chains. So where you have blocks that are coupled and need to move together, or where you have blocks that are more sparse, like RAM blocks and DSP blocks that are more rare. It's better at figuring out Where should I move these to make sure I'm getting a sufficient diversity of perturbations, but I'm also, as placement proceeds, trying to do things that are more local. Okay, so that results in a big gain versus VTR8. How does that compare to commercial tools? So we can only do an approximate comparison here, but we did an approximate comparison to Quartus 18.0 because we have an approximate capture of Stratix 4. Now, all the details of Stratix 4's routing architecture, et cetera, have not been released, so we can't do a perfect capture of it. So we should only interpret these as kind of a coarse comparison, not a perfect comparison. But overall, runtime is in a pretty good state. So comparable in packing and placement, a bit better in routing, and the overall runtime is actually a little lower than Quartus, and the peak memory is about the same. So in the same ballpark for runtime and memory usage. In terms of quality results, in terms of resource count, it's pretty close. Actually uses a little bit less in terms of most types of blocks. Tends to use more small RAM blocks, fewer large RAM blocks. There is still a gap in routed wire length and in critical path delay. Okay, it's much better than it was in VTR 7, where these gaps were much larger, but there's still a 20 to 30% gap in these metrics. So we haven't fully achieved the same quality as Quartus on this architecture. Okay, so that was where VTR 8 stands. Let me talk about an enhancement we've made since VTR 8. So it's not in that comparison, it kind of goes beyond it. And that's applying reinforcement learning to placement. Okay, so the usual way that you develop a CAD tool is, you have a very large solution space, so you use all sorts of heuristics. Most of our CAD problems we can't solve optimally. So a graduate student or an engineer comes up with an idea, codes that up in a tool, evaluates that by running a bunch of benchmarks through it, and it almost never works very well at first. So you tune it. And you go through this loop many times, and gradually your grad student or engineer becomes less happy because the tuning and evaluating is taking a long time and most of the results are negative. This also means that the heuristics you use, you have to keep, you can't have too many knobs in them usually because you just can't tune them all. So you have to be careful about how many parameters you put in your tool. You also tend to tune for the average case because you have a suite of benchmarks, you tune on that. That's already a lot of work. It's difficult to investigate every benchmark design and start trying to tune even more finely. So the overall idea of reinforcement learning is to try to get the human out of most of this loop. So the human still comes up with the idea. I got an idea for an enhancement or a new CAD algorithm, but now the tuning is done automatically by an agent that somehow has to measure a reward from this tool as things are happening. And based on what reward the last action taken gave, the agent decides what's the next action I should take. And this opens up the possibility that we could have better heuristics because they could have more parameters. They could exploit more information. They could adapt better to the design, even online, as you're actually optimizing the design, and get better than the average case. Okay, so it's intriguing, and we've been working on it within the placement engine of VPR. So as I mentioned, that's a simulated annealing placement engine. So it modifies placement by making moves, and then it accepts or rejects the move based on the cost change. Okay, so if you perturb from what we have on the left, you rearrange these blocks and you get what we have on the right, and the estimators of wiring and timing say that it's a net gain. Your cost change will be negative, and you'll accept it. And if the cost change is positive, meaning it appears to have degraded your placement, there's still some chance you'll accept it. Early on, the chance is pretty significant, but over time, the temperature parameter that controls how likely you are to accept degradation drops, and it becomes less likely. Okay, so that's a well-known algorithm, but there are a lot of different enhancements that you can put on top of that. So I talked about perturbations. So there are many different perturbations that you can put in a framework like this. So you can have simple random swaps where you just move things randomly. You can make that a bit smarter by saying I'll try to make random changes, but not too disruptive, especially if we're down at a low temperature. You can have smart moves, and there are a variety of things that have been explored in industry and published in academia of different smart moves where you examine the current placement or a part of the current placement and propose something that should minimize wire length or improve timing. Okay, and there are a lot of different proposed smart moves. You can have even more complex moves. So you could run an analytic placer, which is a matrix formulation, to minimize some function on a portion of your placement. You could do an assignment operation. So an assignment operation looks at a bunch of blocks at once, and if it ignores the interactions between them, just considers the interactions to the rest of the placement, it can basically produce, this is the best place you should put these, for example, for wire length. So we could run that on a portion of the placement as well. And any one of those could be considered a move. So traditionally, many of these haven't been considered moved in simulated annealing, but we want to think of them all as moves in simulated annealing. But as you expand your menu of what you can do for perturbations this way, you've got a lot more parameters. How often should you make different moves? Should that depend on the circuit, or how far are you along in the anneal, or other things that are happening? Some of these moves can be quite expensive. So running, for example, an analytic placer on a part of your placement or an assignment operator could be much more expensive than a simple random move. So you have to take into account as well that it's not just what's the probability you've got a gain, but how long did it take you to do it? Because that's going to affect how often you can make a move of that type. So the idea is to treat that as a reinforcement learning problem. Can we get the algorithm to figure this out? So we built a reinforcement learning move generator. The actions are, actually this is not quite right. Early on, basically, the actions were just what kind of block type do we move, but now in the work I'm going to show you, it's more than that. It's also what kind of move. So it could be kind of classic random moves. There's a type of move called the median move that optimizes wire length, type of move called critical region that tries to straighten out critical paths that improves timing, and more, right? So I'm only telling you about a few of the moves. So we coded up a whole bunch of different types of moves, some from the literature, some ones that are variations or new, and then have the reinforcement learning agent try to figure out when should I use these on different circuits and at different points during optimization. We experimented with a few different reward functions. The one that worked well, this is one that worked quite well. The final one we use is a slightly more complicated version of this. But basically, if a move is accepted, the reward is the cost gain, so the negative delta cost, divided by the time it took, or an estimate of the time it would take. So we care about how much do we improve things, and also we cared about how long it took us to evaluate that move. We actually found it was better to not penalize the move generator when it didn't find an improvement. We just gave it a reward of 0. If we gave it a reward that was negative when it proposed a move that was not taken, then it didn't try enough hill climbing. So we tended to find that this was better. Okay, so that's the reward. The agent, we played with a few different agents, but basically they estimate the value of the actions by monitoring this reward and select what action to take at every point. So it's basically learning how to tune. So how well does it work? Well, so I'm showing you here 3 curves, and every point on these curves is basically an average result on that entire Titan benchmark suite. And we've tried this on other benchmark suites as well, and they give very similar results. So the red curve is, actually, I'm going to start in the other way. The red curve is VPR 8, okay, before we put this reinforcement learning agent in. And it's an entire curve because we can actually do more or fewer perturbations, and we can basically make the placement engine faster if we don't do very many perturbations, but it gets a lower quality. So the estimated wire length is higher, and the estimated timing is higher. Or we can have it do more perturbations, and we get a higher quality answer. So each of these curves is basically sweeping across that runtime versus quality trade-off space. If we put in a bunch of these smarter moves, we get the green curve, okay? So we put in smarter moves, but we basically have a random agent. The agent doesn't learn. It just basically is picking a fixed fraction of each of these different kinds of moves. It does actually help wire length. Some of these more advanced moves are very beneficial for wire length. It actually hurts the critical path. Turns out that sometimes it's doing too overly disruptive things late in the anneal. So you can see this green curve is worse for wire length. When we put the reinforcement learning agent in, we get the blue curve. So it actually learns how to best exploit these different moves that we put in, and we get an overall better result. The wire length curve and the timing curve shift down and to the left. So the tool becomes faster and gets a higher quality result, basically at every single quality point. So that's why I'm showing the entire curves. Okay, what happens? That's an entire curve. Another way we can evaluate this is just pick a default. We're just going to pick an effort level, how many perturbations to do for both the VTR 8 annealer and this new reinforcement learning one. And this is I'm showing you a few of the designs from the Titan benchmark suite, along with an overall average on the whole benchmark suite on the right. Basically, we can do fewer perturbations and get equivalent quality. So we can get the same wire length, same critical path delay, but we can take 44% of the runtime. So it's working quite well. And that's what's basically checked in now as the default placer in kind of the most recent master code for VTR. Ongoing work is to make a more complex RL agent and to combine offline training with online learning. So right now, the agent learns completely online. It starts off placing a benchmark with no knowledge of what to do. It's just monitoring the rewards of what's happening to figure out what to do at various points in time. We found that to work well, but we think we can do even better if we basically give it a better starting point by doing some offline training in advance. So we're working on that right now. Okay, so maybe that's kind of recent progress in VTR. I'm now going to talk about 3 things that are underway for VTR 3D, which is the name for basically a bunch of upgrades to VTR for the Crossroads 3D FPGA research project. First one, which is a big one, is to make VTR optimized for embedded NOCs. So the Crossroads FPGA is envisioned to be a multi-die system with an FPGA fabric die that is, maybe different than today's fabrics, but at a high level, it looks like an FPGA, feels like an FPGA. But that is linked with a base die that's connected through silicon vias that has an embedded network on chip, so that we have a new coarse-grained interconnect that we can use to link things, and has a variety of heterogeneous blocks. So accelerators, memory, that's part of the Crossroads project, is to figure out what's the best stuff to put on that base die. So the NOC is really a key part. So we need to target it inside VTR. So how do we do that? Well, we're going to build on prior research. So there are a bunch of publications by my group and others on this. One of the key things that leads us to believe is a good idea is we're going to treat the NOC from a logic level as a distributed FIFO. You connect to it. It's like a FIFO, but you get on the FIFO at one spot and get off the FIFO at a different spot. So that's kind of shown over here on the right, right? We have this fabric interface. And for VTR 3D, we're making that fabric interface AXI compatible and making sure that we harden the logic needed to cross clock domains and so on, so that you can do near glueless connection of soft logic to one of these routers using a standard interface. Okay, then we need the place and route engine to actually decide how to use this NOC. That's how you hook it up in your design. So we're going to place all of the blocks, including these routers, in a unified step. It means that how you're using the NOC and how you're using the conventional FPGA interconnect to combine your soft modules, they're not independent problems, they're coupled. So as we decide where to put the soft logic, we're simultaneously going to be choosing which router in the NOC do you connect to. To do that, we need to augment the placer's wire and timing goals, which it already has, with new goals, NOC latency and congestion. So we're going to need new design input. So we'll add expected traffic flows and constraints on latency for those flows. Now, how do you get those flows and how do you come up with those latency bounds? Well, perhaps a designer just knows if I use this latency, it will be okay. So in that case, it's easy to write them. But commonly, we don't think people will know what exactly those constraints should be. So we're building a separate simulator, System C-based simulator that will help analyze and estimate NOC latency and congestion. So you can basically test if I have these constraints, is my system getting good throughput? It's essentially the NOC equivalent of a timing analyzer and timing constraints. After the place and route engine is done, it will output the router locations along with the locations of everything else and the packet routing algorithm. So we'll have configurability in how we actually choose to route the packets through these routers. And that's another research question. What are the best ways to do that? So that's like another additional CAD step. Once you've chosen where to put the routers, what would be a good set of routing tables to program into them to optimize your NOC? We're also working on placement quality. So placement quality, I've talked about, we're using reinforcement learning to try to improve that, and that's working well, but that's not the only thing we're doing. It's going to give you a very high-level flowchart here. We are working with David Pan's group at the University of Texas at Austin to integrate with ElfPlace, which is a state-of-the-art analytic placer. You can read about it in Transactions on CAD 2021. Its strength is extremely high-quality wire length optimization with good runtime. We want to integrate it with VTR and enhance its architecture flexibility, because its architecture flexibility is currently it targets a specific architecture. So increase that, bring in a bunch of the constraints that we have in these complex architectures with carry chains and DSP chains and heterogeneity and NOCs, make it timing driven, and basically get the best of both worlds. So I'm showing some of the links that will be going on between those tools, where we're basically passing constraints and netlists into ElfPlace, and it's passing back placement information that will affect both the packing and placement. So one of the strengths of ElfPlace is that it actually places the primitives, so there's no barrier between packing and placement. We want to take that flat placement and use it to affect both the packing and the placement in VPR. The packing of VPR's strength is that it understands a lot of arbitrary legality and interconnect constraints. So we want to take the ElfPlace results as essentially guidance so that we can still legalize the result for a wide variety of architectures. And the last enhancement that's underway is to support Research Vector 5 of this Crossroads 3D FPGA project, which is partial reconfiguration. So the NOC gives, as James talked about last week, the network on chip gives some really interesting possibilities for partial reconfiguration. You connect to the NOC in a standard way, and now you are through it connected to the entire chip. So that really is very interesting. So the NOC work links to partial reconfig in that way. But the other thing we need for partial reconfig from a physical point of view is we have to be able to constrain where do we put various parts of our design so we can swap them in and out. So we're building floor planning constraints into VTR, and basically they'll allow arbitrary regions. So this L-shaped region that I'm showing here would be fine. Okay, so to summarize it, VTR is an open source, flexible CAD tool that's very useful for enabling both architecture research for FPGAs and CAD research by the community. It's large and it's an active open source effort. So it's more than 12,000 commits, more than 100 distinct committers, and these numbers keep going up. So these numbers are a few months old. They'll be a bit larger now. It's also linked to other open source efforts like SymbiFlow, which is targeting commercial FPGAs with open source tools, OpenFPGA, which is about taking VTR architectures and automatically laying them out so you can move to an embedded FPGA or a custom FPGA very quickly. And you can mix and match your flow. So I've shown a couple of flows in this talk, but there are other ones. So some of those flows, for example, connect the Yosys synthesis tool into VPR for placement and routing. It's flexible, has good but can be better result quality. Welcome contributions. So if you kind of are intrigued by this, go look at the source code, and hopefully open source allows us all to make a contribution faster. And that's the end of my talk. Thank you.